Energy of a few charges. When you want to bring a few charges to a position or to a location, you have to spend some amount of energy and you have to work on it, right? And that was equal to Z1, Z2, right? E squared by 4 pi epsilon R over R, right? That was the energy of a charge accumulation, of a charge distribution. You can also see in Griffith, they have a good article on energy of a charge distribution. Right? You can, if you are very much interested in, so you can go to Griffith for the energy of a charge distribution if you want to see in detail. Okay, let us do an example, right? And that will be force needed to break a sodium chloride molecule. Right? Energy needed to break a sodium chloride molecule, right? Such that the separation between the sodium and the chlorine ions is approximated at this nanometer, which will be to 2.7 angstrom, right? That is the separation between
bond length.
between a sodium ion and a chlorine ion, right? The sodium will transfer its electron to chlorine because chlorine is more electronegative and that will attract the electron. So sodium will become plus and the chlorine will become negatively charged. We say that this is an ionic bond.
Yes.
So the force will be like an attractive force, electrostatic attractive force between sodium and chlorine. So we can use this electrostatic energy equation, right? Z1, Z2, and E squared over 4 pi epsilon R4. Here, the Z1 should be equal to 1 and Z2 should be equal to 1 because both are singly charged. Right? The number of charges here is 1. So Z is equal to 1 and Z2 is equal to 1 because there are only singly ionized.
Yes.
Right? There is only an electron transfer, a single electron transfer. So this is equivalent to 1, the charge is equivalent to kind of 1 proton and this is equivalent to 1 electron. So we take Z1 is equal to 1, both are equal to 1. And similarly, the relative permittivity will be equal to 1 because it's the permittivity of the medium compared with the permittivity of free space. And here we consider the medium A is air. So therefore ER will be equal to 1, right? And the permittivity of free space equal to 8.85 and 10 to the power minus 12 coulomb squared per meter squared, right? Or Farad per meter. Right? So we would like to put it there. So W will be equal to 1.6 and 10 to the power minus 19 whole square, right? Coulomb square and 4 pi, right? And 8.85 and 10 to the power minus 12, right? And coulomb square per meter square, and the distance, right? This one.
0.2.
Yeah, the distance will be 2.7, right? 10 to the power minus 10
10.
meter, right?
Yes.
So when we do the calculation, comes out to be equal to, and look, this is one is negative charge and the other is positive. So we can put a negative charge here. One is electron, the other is a proton, right? So minus 8.4 and 10 to the power minus 19 joules. That is the energy of a sodium chloride molecule. And from the negative sign, that's we can say that as an attractive.
That we will give this type of this much energy.
Yeah, this much energy should be given, right? The negative sign shows that this is an attractive energy, right? Lower potential, we call it lower potential, right? Attractive or a stable situation, right? And you know the energy is, the negative sign is just to show us some meaning. Otherwise, this energy is needed. 8.4 and 10 to the power 19 joule is needed to break a
Bond.
sodium chloride molecule, right? Here in molecular physics, right, there is another unit that is famous. In molecular physics, we have another unit, and that is called the KT.
Yes, energy.
Yeah, we use energy. We measure in molecular physics. Energy is measured in KT. Yes, sir. Yes, this one where T is equal to 300 K, which is the room temperature.
Yes.
And K is equal to Boltzmann constant.
Boltzmann constant 1.38.
Boltzmann constant, and that is equal to 1.38 at 10 to the power
Minus 23.
minus 23 joules per Kelvin. 23 again.
Yes.
So 1 kT energy, 1 kT, right? What is, how much is this energy? How many joules in this energy, right? That is 1.3 and 10 to the power minus 23 multiplied by 300. And that will be equal to, right? This is about 1.4. So it's about 4.4 or something like that. Right? Here I have written 10 to the power minus 21, right? And joules.
Yes.
Right? This many joules of energy. 1 kg is equal to 4 times 10 to the power minus 21 joule. Right? Okay, so 1 joule is equal to, I will just
Divide.
divide it by that, and that comes out to be 2.4, right? And 10 to the power 20 kg. 1 joule is equal to, so kT is the appropriate unit at molecular level. Like a single cetaso pagari gizai. No, regarding safar khalak per kilometer of cafe. Meter ke banari, aksar hai kilometer of kilometer. No, our kilometer appropriate unit है. और तो जैसे चीज directly जाने हिसाब के गाँव किलोमीटर खबर है किलोमीटर खबर है. So the appropriate unit at molecular level is generally they talk about kT. This much kT of energy instead of saying joule. So 1 joule is equal to that much of energy. So kT is really a small unit. So how much is this energy? Equation 1 plus how much is this energy? Right? This 8.4 and 10 to the power minus 19 joules, right? So that will be equal to 8.4 10 to the power minus 19 multiplied by 2.4 and 10 to the power 20, and that is equal to 200 kT. So this much energy is required. 200 kT is required to break the sodium chloride bonding. 200 kT, right? That much is required. How much force is required to break the bond? So we know that omega, or W, whatever you call it, that is force multiplied by distance.
Yes, sir.
Because we say work is the product of force and displacement.
Yes, sir.
So force is the division of work divided by
D.
is D, right? So force will be equal to, right? And the distance, which is the separation, right? 2.7 and 10 to the power minus 10. So 200 and 2.7 and 10 to the power minus 10. And that comes out to be, right? If this is in kT, then you can change it back. Since this is an angstrom, this is a meter, you can change this back to, that is kT, right? In kT. And this is in meter. So you can change this back to
kT,
the SI system, to joule.
Yes, sir.
Then that is will be equal to 8.4 10 to the power minus 19 joule divided by this thing, which comes out to be, right, 3 nanonewton. 3 nanonewton. So this much force is required, right, to break the, or we can, if there is another way of this, you can put a negative sign over here, negative sign over here, negative sign over here, and negative sign over here, and this will mean that the force between them is attractive.
Yes, sir.
So if you have to break the bond, so you have to apply a positive force so that the net result is 0. And the ions will be free, which means 0 force. Right?
Sir, the force will come in. The room temperature man was doing force for the provide key.
No.
That will be
room temperature माने होता है कि
like let's suppose.
ना करना बोरा होता है.
जी sir.
जब हम सर देख ना room temperature माने यो kg है. Minute. Then 200 kg required.
Nasa the force है रोमा.
No force देना रहा है. अगर हम तो बोरा 10 months सर energy सुनो ना 1 kg ला. Room temperature माने. So they bond in some 200 times. तो this is 200 times energy बता रहा तो मेरा का सेंचुरी टेम्परेचर पाएगा अलग अलग आती है
Yes.
सब कुछ है
Yes, sir. Yes, sir.
Okay. We are estimating electrostatic forces. Now, towards our understanding or making our background, we also want to see different situation in which the electric forces or the electrostatic forces exist. For example, the force between two, right? Plate charge surfaces. Two plate charge surfaces, right? We have two plate charge surfaces. Suppose one is like plus positively charged, like, do you remember the parallel plate capacitor kind of situation? So this is like, we call this has a surface charge density negative.
Yes.
And this has a surface charge density of sigma. Sigma and minus sigma. So from the field theory, we will say that one charge body interacts with the field produced by the other.
Yes.
Say that? So there will be a field. A field will be away from the positive and towards the negative. Right? And similarly from here it will be like this.
Yes.
Right? Here it will not be like parallel lines like this because on this side we do not have a plate. So it could be like maybe like something like if this is a very long, these are very long plates. Suppose we say they are very long plates, then they could be like parallel. But if they are not long, then they can curve here.
Yes.
Somebody else say it?
Yes.
So the electric field produced by suppose this one, right? The one will be equal to minus sigma over 2
Epsilon.
epsilon and epsilon r. Right? We write r as well for it. We write these two for epsilon. So that is the electric field because of a single
Plate.
parallel, a single plate plate, right? And the force F will be, right? This electric field multiplied by the charge,
Charge.
right? So it will be minus sigma 2 epsilon r and epsilon naught, and multiplied by the charge q, and that will be minus sigma 2 epsilon naught epsilon r, and this charge will be like sigma into A, where A is the area of the plate,
Yes, sir.
right? So this comes out to be minus sigma squared A by 2 epsilon naught epsilon r. This is F is equal to that. So that is the force between two plates separated by some distance d, suppose, where the area or the dimensions of these plates are very much greater as compared with the separation.
Yes. Yes.
So now, look at this. This force is independent of the distance. It's because we consider the plates to be very long, and the lines of force are all parallel. So when the lines of force are parallel, the field is uniform.
Yes.
When the field is uniform, so it is working or interacting with a single charge, anywhere it will have the same force.
Yes.
So therefore, there will be no dependence of
D.
force on the separation or the. Let's if we have a single charge here, positive charge. So we say the field lines are like this. So look, here the field is stronger, the lines are closer. Here the field is very weak because there is no line here, the same area. So here the field is weaker, the field is stronger. So here there will be more force and there will be
Less.
more. So force depends upon distance here because the field gets weaker and weaker as you go away from the charge. You know what I'm saying?
Yes, sir. Yes.
So therefore, in this plate, the lines are all the same separation. The density of the lines is the same. Therefore, no dependence on the separation or the distance between the two plates. Now let us see double square. Berapa nih besar awal? Now we are going towards polar molecules. Right? Charge is now shifted to polar. So the dipole moment, we are going toward the dipole moment or toward the polarized molecules or polar molecules and the force between them. Right? So interaction of polar molecules. Interaction of polar molecules. Interaction of polar molecules. Let's first know what is a polar molecule, how it can be produced, and what are different definitions, concerned with polar molecules, and what are different factors that are that we will use. So the first thing that is associated with polar molecules is a dipole moment. And a dipole moment is a measure of, right? It's a property. Dipole moment is a property. It's a measure of how much polar a molecule is. Dipole moment ज़्यादा भी, polarity ज़्यादा था. Dipole moment कम भी. The dipole moment is a measure of the polarity of a molecule. Dipole moment is the measure of the polarity of a molecule. Right? Like sweetness is the measure of, what should I say? You want to measure something like वजन बजूया में सागर योशीस mass मुतालिक ज़्यादा लगे mass ज़्यादा वजन में ज़्यादा. It's, I don't know how should I explain it, but it is a measure of the polarity of molecule. A wazn is a measure of how heavy the body is. So and measurement of a dipole moment, right? So for mathematical purpose, we say it is the distance between two charges multiplied by the amount of a single charge. When two charges are separated, right, by some distance, and that is minus q, and that is plus q, then the dipole moment is defined by the separation multiplied by the amount of a single charge, right? And we say, what is an elliptic dipole? An elliptic dipole is actually the assembly of two charges separated by a small distance. Two opposite charges, equal and opposite. Two equal and opposite charges separated by a small distance, they form a dipole. Dipole, electric dipole. We call it an electric dipole. Two charges equal and opposite separated by a small distance, right? Okay. There is also a molecular dipole moment, right? Molecular dipole moment. Right? Some atoms are more electronegative,
Yes.
and some are less. For example, if we talk about the H2O molecule, right? So if that is oxygen and that is hydrogen and hydrogen, right? So the oxygen is more electronegative and attracts the bond, the pair toward itself. So it will become like something like this, and that will be left with a positive net effect of a charge, kind of, right? So in this way, this molecule, this becomes polar. Hello? Hello? What's hey? We have a water molecule, so that will be kind of a positive charge on this side and a negative charge on this side. So this can be considered as an electric dipole, which we will attribute to a molecule, right? And this is the direction of dipole moment. It is from the negative charge to the positive charge. Now, what is the unit of the electric dipole moment, right? The unit is dpi, right? Dpi is the unit of the electric dipole moment. And 1 dpi, right? 1 dpi is the dipole moment of a charge, right? Of a charge of 1 state coulomb, and a state coulomb, right? Ten to the power minus 10 state coulomb. Dpi is the electric dipole moment of a charge. I would say it is Q and Q D. So how much charge? 1 dpi. The charge is 10 to the power minus 10 state coulomb. And the separation, right, 1 angstrom. 1 dBar is the electric dipole moment of a charge of 1 state coulomb each, separated by 1 angstrom. And state coulomb is the other system, the electric units in the CGS system, that in some physics books that very much used. So it's equal to, right, 10 to the power minus 10 multiplied by 1 state coulomb is equal to 3.35, and 10 to the power minus 10 coulomb. Right? And that will be 10 to the power minus 10 meter. So 1 divide R1D, that is equal to 3.35 at 10 to the power 3.34 and 10 to the power minus 30 coulomb meters. Right? 1 dBi is the unit of electric dipole moment, and that is equal to, if you convert this to the SI system, then that is the SI system, right?
Yes, sir.
So in SI, 1 dBi will be equal to 3 and 10 to the power minus 30 coulomb meter. Okay, let us do an example, right? Right? Dipole moment, right? How much is the dipole moment of two charges? 1.6 10 to the power minus 90 coulomb and minus 1.6 10 to the power minus 90 coulomb. These are two charges. We can say the electronic charges, right? Two electronic charges. So, two electronic charges and separated by a distance 0.1 nanometer, right? We can say 1 angstrom. Two electronic charges separated by how much is the electric dipole moment, right? So we will say U is equal to G, right? That is equal to 1.6 and 10 to the power minus 19. And we can say 1 10 to the power minus 10, right? And that is equal to 1.6 and 10 to the power minus 29 coulomb and meter. Now, we know that what we will say, we will decrease coulomb meter. So coulomb meter here, then our system here, coulomb meter will be equal to 1 over 3.34 and 10 to the power 30 dBar. So then we put it there, right? So it will be equal to 1.6 10 to the power minus 29 multiplied by 1.3.34 and 10 to the power 30. So divide. So 1.6 divided by 3.34, that will give me something like, I multiply by just 10 to the power minus 29, that is 30, so 110 here. So it's like 4.8 dbar. The electric dipole moment between two charges. Let us finish here.